Okay, the next example is example 5D. All right, so here it is. Read it to you. Suppose that the number of people entering a department store on a given day is a random variable with mean 50. Suppose further that the amounts of money spent by these customers are independent random variables having a common mean of $8. Finally, suppose also that the amount of money spent by a customer is also independent of the total number of customers who enter the store. So let me write down some of this here. So N is the number of customers entering. We're told that the mean is 50. And then let's say xj is the dollars spent by the jth customer. Should probably lock that. Okay. We're told that that is a mean of 8 for all j. And we're told that n and the dollars spent, all of these, this whole family of random variables are independent. Okay? And what do we want to know? What is the expected amount of money spent in the store on a given day? So let's say y is the total money spent that day, and we want to know the expected value of y. Okay, so y is the total spent, so we're going to add up the amount spent by all of the customers that enter, but there are capital N customers, and I'm adding that up. Okay. Now, here's what makes it tricky, is that I've got a random variable inside the limits of my summation. So I can't say that the expected value of the sum is the sum of the expected value. Right? The expected value of this is what I want. And it is absolutely not equal to this. Because this thing here, that's a real number. Whereas this thing actually just equals 8n, and it's a random variable. So a random variable and a real number are, not the same thing. So, and the reason that you can't do this is because you've got a random variable in the limit of the summation. So it's just not going to work. Okay, so how do we get it out of there? One way that you can get it out of there is by conditioning on n, on capital N, and this is what they do in the example in the book. I'm going to let you read that one for yourself, and I'm going to do it a different way. That way you'll see it both ways, and you'll have two things that you will have learned. So one way to get rid of that n is to say that y is equal to, and then write it like this. The sum as j goes from 1 to infinity of xj times the indicator of the event that capital N is bigger than or equal to little j. Right? So this indicator random variable right there will be 0 when j is bigger than n. And so we're just ending up making it a finite sum anyway, and it is exactly equal to this. But because I've written it this way, I no longer have a random variable in my limits of summation. Okay, so I can say that the expected value of y is equal to the expected value of the sum as j goes from 1 to infinity of xj times this indicator. Okay, now, what I'd like to do is say this. Well, now the expected value of a sum is the sum of the expected values. But here I'm kind of breaking the rules. I'm not really using the theorem from our book, because the theorem from our book says that you can do this when it's a finite sum. It doesn't say that you can do it with an infinite series. So we don't have a theorem that says that I can do this. So I know that this is okay, and I know it's okay using a theorem that is beyond our course. And one reason that I know it's okay is that it comes from something called Fubini's theorem, or really what I'm using is a special case called, well, it's not really a special case. It's like a sister theorem, Tonelli's theorem. It goes beyond our course, but the fact that you could use here to do it is that if the random variables that are the terms of your series, if they're all non-negative, then you can always swap the sum and the expected value. And here they're all non-negative. The indicator is either 1 or 0, and xj is money spent. So it's part of the hypothesis. It's sort of an implicit hypothesis that they're not owing money to the department store. They go in and they spend a non-negative amount of money. So if my random variables here in my series are non-negative, then I can swap them. All right, so if I've got this swap, now what is this? The expected value of xj times the indicator that n is greater than or equal to j. Well, xj and n are independent. So xj and this indicator are independent. And the expected value of the product of independent random variables is the product of the expected values. Okay. This here is 8. I can pull that out. And here I have just the probability that n is bigger than or equal to j. And this quantity you should recognize. We have a formula for that we've seen a couple of times, at least once before. That is one way of calculating the expected value of n. So this is 8 times the expected value of n. The expected value of n in this problem is 50. So $400 is the expected total amount of money spent in the store that day. Okay, so that was example 5D. There are lots of other examples in here. I would encourage you to read through them, as well as reading through those supplemental notes. I want to jump ahead toward the end of this section to, how far is it? I gotta go all the way to conditional variance. So conditional variance, we talked about a conditional expectation, but we can talk about the variance of the random variable x given the random variable y. And the definition is the expected value. Well, actually, let's before we do that, review ordinary variance. The variance of x is, but the definition is, it's the expected value of x minus the expected value of x squared. And then you can do some work and derive a formula that the variance of x is the expected value of x squared minus the expected value of x squared. Okay. Conditional variance is defined similarly, except you see how in the variance definition there are two expectations. So in the conditional variance, both of those expectations are going to be conditional. So I have x minus the expected value of x given y, that whole thing squared, and then that whole expression given y. There's my definition. And you can similarly go through and do some work and derive an alternate formula that says that it is equal to the expected value of x squared given y minus the expected value of x given y squared. Now, the conditional variance formula is proposition 5.2, and it says the following, that the variance of x is equal to the expected value of the variance of x given y plus the variance of the expected value of x given y. This is the conditional variance formula. So just like we had, so if you go back and we looked at all these examples where I guess I did this one, it's 5D, I did it in an unusual way. But the way that we've been doing all these examples before is computing an expectation by conditioning on the inside by something else. And this formula we have here now gives us a tool for computing a variance by conditioning on the inside by something else. It's a few lines to derive the conditional variance formula. If you look in your book, it's proposition 5.2, page 354. They show the derivation directly in the paragraph directly above that. I'm going to direct you to look at that on your own, and I'm going to immediately go to an example. Which example am I going to do? Example 5P. Okay, so let me read it to you. 5P, page 354. Suppose that by any time t, the number of people who have arrived at a train depot is a Poisson random variable with mean lambda t. In other words, what they're trying to say is that n of t, so this is the number of people who have arrived at the depot in the time interval 0t, and n is a Poisson process. We talked about the Poisson process with rate lambda. Remember, one of the properties of a Poisson process with rate lambda is that n of t has a Poisson distribution with parameter lambda t. Okay, then the example continues. If the initial train arrives at the depot at a time, independent of when the passengers arrive, that is uniformly distributed over 0 capital T. Okay, so y is the time that the train arrives. And y has a uniform distribution, uniform on 0 capital T. This is just a constant. Even though it's a capital letter, it's not a random variable. It's just a constant. Okay, and y and n of t for all t, this whole infinite family of random variables. It's an infinite uncountable collection. You've got, for every t, there's a random variable n of t. There's already an infinite collection. Throw y into that infinite collection. We're assuming that all of those are independent. Okay? What are the mean and variance of the number of passengers who enter the train? So what is the number of passengers that enter the train? Well, I think we're supposed to assume that everyone who is there at the depot is waiting for that train, and when the train arrives, they all get on. So the train arrives at time capital Y, and at time capital Y, the number of people who have arrived is n of capital Y. And so we want the mean and variance of that. So what's the expected value of n of y? And what's the variance of n of y? Let me give it a name, just for notation's sake. Z. I don't know, maybe not Z. I usually use Z for a standard normal. What should I call it here? I'll call it Boy, wow. It's so weird to just deliberate for so long on picking a letter. You'd think I would just be able to pick one. I think my made videos for so long, my brain is just a little bit scrambled. Let's go with oh, I don't want to get fancy. Okay. Oops. All right. Number of passengers that enter the train. I'm just going to call it V. No, V is terrible. That's like variance. Man, live. Okay. How about L? Makes no sense. Why L? It doesn't stand for anything. It's going to be L. L is N of Y. Here I am sitting alone in a room, recording a video, laughing about my own stupidity. I am really losing it here in this quarantine, it seems like. But at least I have toilet paper. Okay, L. What is the expected value of L? Well, all right, so what we can do is, so the expected value of L is the expected value of N of Y. And I can condition on the inside by capital Y. Capital Y is uniform, so it's continuous. So I can write that as the integral, negative infinity to infinity, of the expected value of N of Y, given that Y equals little y, times the density of capital Y. Okay? Capital Y is, what is it? Uniform 0 to capital T. So that's going to be, oops, I'm just going to be integrating from 0 to capital T, and the density on that interval is 1 over T. Okay, and now what is this? Well, Y and N are, capital Y and capital N are independent, so I can just drop the conditioning and replace capital Y with little y. But this, now if little y is not a random variable, then this is Poisson with parameter lambda y. So that means that the expected value is equal to its parameter. All right. So I have, I can pull out the lambda, I can pull out the t, and I have the integral from 0 to t of y dy. And then we can calculate that. But you know what? That is one way to do it. And in this case, it might be easier to think a little more intuitively. So let's skip all this integration. Let's start right here and come down and do it a different way. Look on the inside there. The expected value of N of capital Y given Y. If we're given little y, then capital N of, if we're given capital Y, then we know that's the parameter, and N is a Poisson process. So this is lambda times capital Y. Right? Or another way to think about that is, if you come up here and you look at this expression, we calculated it, right? It's here. It's lambda little y. And this thing is what you get when you plug capital Y into this expression. So it's got to be lambda times capital Y. Well, then we can take that thing and plug it back up right into here. And so I get that the expected value of L is the expected value of lambda times Y. Lambda times the expected value of Y. Y is uniform on 0t, so its expected value is t over 2. So I've got that. All right, we can go on and get the variance. All right, so what's the variance of L? So for the variance of L, I can use the conditional variance formula. Right? So I'm going to condition on the inside. Well, so what is this? It's the variance of n of y, and I can condition on the inside by y. So the conditional variance formula says that this is the expected value of the variance of n of y given y plus the variance of the expected value of n of y given y. Now this thing, we had this thing already. It's up there on the top of the screen. That's lambda capital Y. Okay. But how about the first part? Well, so this thing right here, informally, I could say it's Poisson with parameter lambda capital Y. And the variance of a Poisson is the same as its mean. It's just the parameter itself. So this becomes the expected value of lambda y plus the variance of lambda y. So it's lambda times the expected value of y plus lambda squared times the variance of y. Right? Y is uniform 0t. So this is 1 over t, and then you have to remember what is the, not 1 over t, what am I doing here? T over 2. And then you have to remember the variance of a uniform on an interval from 0 to t, and it is t squared over 12. All right, so we get the variance of L is lambda t over 2 plus lambda squared t squared over 12. Okay, and that's it for section 7.5. And I will have more videos for section 7.7. We're skipping 7.6. 7.7, we will do that. And then that's it for this chunk of instructional material. So I will see you in the next video.